Okay, right. So let's begin. Just to confirm again, I'm audible, right?
Yeah.
Yeah, yeah.
Great. So, so I will be I want to cover a few ideas in combinatorics today, starting with inductive ideas. So I'll be going towards the combinatorics side. It's possible to you have many questions in basic algebra, in manipulation of variables and stuff like that, and recursion, which can all be done using induction. And these questions usually come in PR more, or AMC, AME, stuff like that. But I will be concentrating on applying induction in combinatorics, and the use of induction is often more subtle. It feels a little more direct when you usually have some sort of expression and you're supposed to prove something on in. Um, and often you actually have to figure out what to induct on, things like that. Um, so yeah, so that's one big thing. And induction can be applied in various ways, right? So just to be on the clear side, you can, your basic form of induction, it doesn't really matter. Induction is mostly common sense, but um, we can say write different statements. One is regular induction, and so that's regular induction is just saying that if you have something that's true for some f of one, where f is a function, variable, um, anything literally. It can be, say, a graph with one vertex, or it can be some structure with only one block. It can be a table with one row, something like that. And if it's true for f of one, and we can prove the statement that if f of n minus 1 is true, uh,
Yeah, then the
then
next one will always be true.
right will be true. It's not as this we are in this statement we're assuming that f of n minus 1 is true, and then we're showing using this assumption that f of n will be true. Then by logic, f of 1 implies f of 2, f of 2 implies f of 3, and so on, right? So one thing you should notice intuitively is that you need some sort of discrete collection of objects, because you're proving some f of 1, f of 2, f of 3, and so on, right? So you need to have a discrete collection of objects where f of 1 corresponds to something with only one something, and figuring out what that something is often the part of the problem. And I might be a little vague, but we'll see a few examples of what I'm talking about. um, okay, and then here we're using this assumption to prove this. So another thing I want to speak about intuitively in this case, the intuition here is that often in a problem where we don't have enough information to proceed, right? We don't have enough information to say something, to tell something. Assuming f of n minus 1, like we're assuming something, right? So there's practically extra power, because we're assuming some statement, and using that we're trying to prove something else. So, and it's the same with proving contradiction too, right? You're assuming something is true and you're showing it's not true. So when you're assuming stuff that might or might not be true, you're actually giving yourself extra power, because okay, wait, is my volume low? Is this the case for everybody?
Yeah, if you talk about
It's
relatively,
low.
I guess it is low. Relatively
Okay.
talking.
Okay, I think I'll try to speak. Um, I'll try to speak louder in any case, right? Um,
Yeah.
yeah. So yeah. So the thing is that here, when you're assuming contradiction, um, right. So when you're assuming contradiction, or in the case of induction, you're giving yourself extra power. even though you're practically doing nothing else, right? You're just using the information in the problem. So yeah, that's a useful thing to keep in mind. And in the case of strong induction, so what strong induction basically means, it's again, induction is all is just common sense. The statement of induction is just common sense. We've just given it a name so that we can remember, to try that form of approach. So in strong induction, the thing is that we still assume, say, f of one is true, or maybe we can assume something like the first f of one, f of two, f of three is true. It doesn't really matter. So we're assuming the first few things or something like that is true, and then we actually in this case of strong induction, we basically have to use the fact, let's say f of one is true, f of two is true, oops, and so on till f of n minus one is true, to prove that f of n is true. Okay, so let me just clarify what I mean here. Um, you're using um, just assuming f of n minus one is true is not enough to prove f of n is true. You need to use the truth of the statements of some things before as well, right? You need to use the truth of some statements, some things before as well, to prove that f of n is true. Um, okay, I know this might be vague, but and some of you have seen this before and you perfectly understand. But we'll come to the example,
Can
right?
you
So
repeat
right, so what I'm
the
saying
last
is
line?
that right, yeah. So what I'm saying is that in the case of strong induction, what it's basically saying is that to prove the truthness of f of n, you will need to assume f of you need to use the truthness of not only f of n minus one but something before. For example, yes, okay, never mind. Right. So say to prove okay, so say you want to prove f of n, and it's a statement such that you need the truth of everything before. So what are you going to do? First, you're going to show that f of one is true. Then to prove f of two is true, you're going to use f of one. Then to prove f of three is true, you're going to use f of one and f of two. To prove f of four is true, you're going to use f of one, f of two, and f of three, and so on, right? Okay, and this might seem a bit vague for anybody who's not seen before, but we have an example here, and don't worry about
Yeah.
that. Right? Yeah. Give me 1 second. Right. Okay. So let's start with this problem. Can you all see this? You can all see it, right? Yeah. So actually, BA mode problems are usually really nice, um, especially the combinatorics ones. Um, so you can all try this for 1 minute, and I'll just explain what it means after that. Okay. Hopefully you all have read the problem, right? Okay. So I just drew up an example of what could be. So what this problem is saying is that you have a bunch of squares. So do try this problem in the meantime. Like keep trying the problem. Um, try the small cases. Oh, let me send the link again. Um, okay, never mind. Guys, give me 10 seconds. I need to go get my charger. This is a little embarrassing. I need to go get my charger. You can try the problem in the meantime. Give me one second. Okay, I'm really sorry about that. Right. So this is one example. So um, did you guys make any progress? Anyone? Okay, just to confirm, I am audible, right?
Yes.
Great. So yeah, this what I wrote on the board is just an example of what one example. So this one, if so, basically a block is colored if um, two out of the three blocks in this part, right? So this part, right? So two out of three colors in that part is um is colored in the previous round. So you'll notice that here you get three, and it's pretty straightforward in any case. The question, if you get used to it. So this is the process, right? So they've given us an algorithm. They've given us something that's changing. They've given us something changing, and they've asked us to prove something about it, right? Now I think I took a session on these kind of things sometime before, a couple 1 or 2 months ago, but generally what we do is we look for invariants or monovariants, and we try to look for the greatest something, the lowest something of sorts. Okay, so we can try that here, but it looks like it's hard to find an invariant. um at first glance you might think that maybe the number of colored solution maybe the number of colored blocks always reduces. Is that true? If that were true, we would basically be done. Is that true though?
What can you uh,
Wait,
again
wait, wait.
repeat?
I don't think I was clear. I'm sorry. So what I'm saying is that if it is true that the number of grayed out blocks or the number of colored blocks, it always reduces by one in each move, at least one. It reduces by one, at least one in each move. Then in n moves, it will have reduced by n, right? So you'll be done. What are they asking us to prove? They're asking us to prove that if n squares are colored gray, then after at most n steps, the whole grid will be white. So if the number of colored blocks reduces by one in each move, um, then we're done. Oh, okay. I'll try to talk even louder. Okay, I'm not sure why. Right. So if the number of colored blocks reduces by one in each step, then we're done because in n steps it will reduce by n, and you'll be done in n steps. Just to be sure, my volume is better now.
Yes, his volume is better.
Great. So
can you wait? I forget the question.
sure, sure, sure. In any case, you can keep the handout next to you.
Yeah, yeah, yeah. I just read a bit one more time.
Yeah, sure.
Yeah,
Right.
okay.
So great. Yeah. So can anybody prove if this is true or not true? Can anybody find a counter example or try to prove that this is true? I'm just trying different approaches. Um, so can you prove that it, or can you show a case where the number of blocks doesn't reduce by one? Maybe it stays the same. Hmm. You can try many smaller examples, and that will give you lots of information.
Yeah, like I am trying small examples.
Great, great. Yeah. Maybe that goes to that. So here you'll notice that if you have something like this goes to this.
I have a question that if gray square is at the corner, then how do we examine that? Like
At
there
the
is no
corner.
square at above.
Oh yeah, no, it's an infinite grid. So I mean, I just didn't
Oh
draw
yes,
it.
yes. Oh, right, right.
Yeah,
I forgot. Yeah, yeah,
yeah, I'm sorry. I just didn't draw anything like that.
yeah, yeah.
But yeah. So guys, look at this. Trying a smaller example, we came upon this, right? Um, so you'll notice that the number of boxes hasn't exactly changed. And this one small example puts
Yeah,
our
yeah.
whole previous approach, it throws it in the bin, right? Now we can't try to prove that at each step the thing reduces by one, because it's clearly not true. Even if it reduces by exactly one in each step, but this step happens in one case, then we're doomed. It won't, the process won't finish in n steps. Is everybody clear so far? Like, um, do I need to clear the question up a little? Anything I said might be vague. Anything? Please feel free to speak up. No, okay. Cool. Um, so okay, so we need another approach at this point. So the thing is that clearly it doesn't need to reduce by one. Can it increase? Can the number of blocks increase? I'm not very sure of that. Uh, but in any case, what approach can you use? So for one thing, we need to. analyze the data given in the question properly, right?
Yes,
So one thing,
it's like the process is that we have to make new grids from the existing one. So induction seems may work,
induction or what?
might work, I guess.
No, like what will you induct on though?
Yeah. So no, it's a process. So we have to find an invariant, I guess.
We can find an invariant, like
Yes, yes.
so we can try to find an invariant. So yeah,
Yeah.
we can try that. I mean, like, although I just have to give you a spoiler, like as far as I know, there isn't any invariant that I know of.
Oh,
Um, so I'm not completely sure of that. The number of blocks, we thought it might be a monovariant, that is, it changes only in one
oh yeah, yeah.
direction, but
Oh,
it
monovariant.
actually
Yeah. Mhm.
it isn't. If that were the case, then we would be done, right? Right, Origin, but induction on what? What do you want to induct on? Like, induction in the statement of induction is in some sense common sense. Some, yeah, so it's common sense, right? But the hard part is often figuring out what to induct on and how to prove the induction. Many times, even proving the statement is easy. The proving the fn minus one, then f of n is true. It's kind of easy. Figuring out what to induct on might be harder. So, what do we induct on? Hmm. So yeah, remember that when you look at Olympiad solutions that say induction, this is induction, you can't really put together induction questions and say these are all the same, because the hard part in an induction question, if it's an Olympiad question, the hard part will be figuring out the setup of the induction. What do you induct on? Etc. Usually. So, one thing. So let's just go back to the question and just look at it again and see what the process is, right? What's the algorithm they've given us? So they're saying that at each step, at each square, examine that square, the square above, and the square to the right.
Yeah, so the square we have to examine is immediate right and immediate above. So, the next one.
So
I mean, we have to examine the next one, right?
go on. Like I didn't understand exactly what you're
No,
saying.
suppose if we have a square, then the process says that we have to examine that square, the square immediate above to it, and then immediate right to it. So this just
Correct.
means that the next square of
The
that.
next squares on the top and the right, but we're not. But notice that we're not looking at the squares on the bottom and the left, right?
What?
Uh, we're not looking at the square to the bottom and to the left of it.
Yeah,
So the thing is that even if you have a square to the bottom and the left, um,
we don't consider it.
yeah, we don't care about it, right?
Yes, yes.
And as a matter of fact, if you think about it, um, um, Ahan, oh wait, 1 second. Origin says induction on the number of black squares. That's a good idea. We can induct, say, assume that, say, three, any square, any, so, so what you can, formulate that as is you take any sort of combination, any ordering of, you put three black squares anywhere, and it will finish in three moves. Then use that to show that, you know any combination of four moves will finish in four moves. So yeah, try doing this. So that's so try doing that. um Ahan says, in the last example you showed the perimeter of the white region is not changing. Maybe we can show that they are it might be a decreasing monovariant. It can't increase, I think. Right, Ahan?
Yeah, yeah, I
Okay, so in this case it actually stays constant too, right? In this case the perimeter stays constant. um So that rule, that's a very nice idea.
Yeah, this
Right?
perimeter idea is quite nice if it works.
Yeah, it's nice, but it's ruled out because of this example. It stays constant, right?
Oh,
And the thing is that if it stays constant in one step, it will stay constant forever. So it might not help us much. Um, Origin, you can try that general idea. That's induction on the number of black squares, right? And just to go back to the idea I was talking about in the question, so the idea we came to was that
you were
the
talking about the
square on,
statement.
yeah, the square on the bottom and the give me 1 second. Yeah, so the squares on the bottom and the left, they they don't matter, right? So
Yes.
um, let me go to that. Um, Say you have a bunch of squares in this region, right? And say you have a bunch of other squares in this region, like that. So, do the evolution of the squares in this box actually depend on the evolution of the squares outside the box? I mean, the thing is, it's no, right? Because um, anything on the bottom and the left can't really affect. You're not taking
Yes,
into
yes.
consideration. Yeah, go on.
No, no, I'm just agreeing that
Oh,
it will
yeah,
not matter.
yeah, right. Yeah, correct. So, it won't matter, right? They don't matter. On the other hand, the evolution of these squares will affect these squares.
Which square? The square which is in the grid.
The squares in the rectangle I drew can affect the squares outside the rectangle, the ones I've drawn.
Square in the triangle kind of. Okay.
Okay, so that is
Uh, by
square.
affecting, you mean that the squares outside the rectangle will become like same colored.
Like, yeah, so when considering if the square can become gray or not, we will have to count these squares inside. But when considering if the squares inside the rectangle will become gray or not, we will never consider these outside squares,
Yes.
right? That's because we're only considering the squares on the right and the top. So for any of the squares inside this infinite part of the grid, you are never actually considering anything outside the grid, right? So you can actually take this
Yeah. Right. Right.
difference. Yeah. Um, so maybe we can split, you know, uh, um, in the spirit of induction, we could split it into two. So, something like if we have a total thing, let me go into some, let me go to a new page. Let me draw something random. I'm really sorry for my drawing skills, right? Something like that. Then maybe, we split it at some point like that, right? So, then these squares, the evolution of these squares, that is, these can depend. Like, let's say we forget about these squares outside. Let's say we forget about square 1, 2, 3 for now, right? What happens to these squares in the inside, right? What happens to these squares in the inside? Um, they change somehow, right? Okay, that's a pretty lame statement.
Yes.
They do change somehow, yeah. But say we're trying to prove the case for the general, like, how many squares have I drawn? 1, 2, 3, 4, 5, 6, 7, 8, right? So I have 8 squares here, right? And say, just like what Origin says, I assume that everything before, right? I assume that any combination of 7 squares, right? Any combination, you put them anyhow, will finish within 7, right? And any combination of 6 will finish within 6, and so on, right? Now, this might seem a very strong statement to assume, right? But in
Oh,
some sense, if we,
well, can
yeah,
you please repeat? You said that in this region, rectangular region, if we have seven gray colored square, then we will remain with seven gray colored square.
no,
Is
no,
that
okay,
right?
I'm really sorry if I didn't explain properly. Let me repeat what I said in the beginning.
Yeah. Okay,
So,
please.
yeah, so we have eight, right? So we have eight gray colored in totally in this entire thing,
Yeah,
right?
including the squares which are like outside.
Yeah, yeah, in everything included, right?
Yes, yes.
What if we can tell, okay, so what if, let me try to explain this differently. What if we can tell that um, everything in this region, that is these five gray squares, right? I've drawn five gray squares, and what if I say these five gray squares will go out, right? In some sense, go out within 5 steps, right?
Go out of this region.
That means
Like,
become completely white. Yeah, become completely white. There's no
i-
gray squares in
okay.
that region anymore,
Yeah. Okay.
right?
Yes.
So
So
what then?
you are like claiming that in five or some squares it will go out of this color is this color region, right?
Yeah, I'm actually doing a little different than that. I'm assuming that's true,
Okay.
right? I'm
Yeah.
assuming that any you take any arrangement of five gray squares, they will
Yeah.
disappear in five moves.
Oh, okay. Okay. Got it.
Okay, and this might seem like a
Yes.
pretty lame assumption, all things considered. But the idea
Yeah.
is that,
Pretty
yeah,
much.
but the idea is that if say we call that assumption f of five, right? If we call that assumption f of five, and if this like, and in general, what I'm saying as f of n is that in n moves, it's basically the problem statement. I'm saying that in if you have n squares in any combination anyhow, they will be completely white in n moves. And if we
Yes.
assume this, and if we're somehow able to show that in this case, say in this very specific case, f of 5 proves, f of 5 is assumed, and we're able to show that f of 8 has to be true because of this. That's because, and why is this helpful? Because after this region, the blue region becomes completely white, then we have these sort of regions, right? We have some sort of very nice rectangles.
So
So
like
what
they
we're,
will also
yeah,
become white by this process if we can prove.
yeah, they will become white very fast because they know that,
Yeah.
after some time, there's not going to be nothing here. There's going to be nothing in the rectangle. And so
Yes.
this rectangle and in this rectangle will have, this one rectangle will have only stuff to the right of it, and this rectangle will have stuff only to the top of it. So, intuitively speaking, these two rectangles will become white very fast,
Yeah.
right?
Yes.
Is everybody else somewhat following me so far? Maybe not having the full idea, but you can put a yes in the chat, something.
Yeah.
Um, Great, yeah. Right. So, okay, amazing. Um, Great, yeah. So, what I'm saying is that if we prove that, okay, it's becoming a little messy, just normal for me, but I'll try not to be messy. Um, where was I? Yeah. So, if we're able to prove that this thing, the rectangle, finishes within 5 moves, right? Then maybe we can show that this smaller one, okay, this vertical column kind of thing, finishes within 2 moves, and this smaller rectangle after in the at the same time finishes within 1 move, right?
Yes.
Yeah. So we're basically done. So and we're actually almost done at this point because, okay,
Because we
let's
can like always continue this.
Yeah. So can anybody try to complete the argument of what I'm trying to say here? It isn't that hard. Just complete the argument. Like first what goes and then what goes. And exactly what rectangle I'm drawing here. Just formulate these things. Just try to think for a moment and try to finish this on your own. And I'll try to be more precise about it. Okay, so let me try that. Okay, so what I'm saying is this rectangle. Okay, so now I'm trying to prove that any thing, right? Any sort of arrangement of 8 squares will always finish in 8 moves, right? And for this, I'm assuming that anything in 7, right? Any arrangement of 7 will finish in 7 moves. Anything in 6 will finish in 6 moves, and so on. This is strong induction. I'm assuming that this is true, right? And then I'm saying split it, like take the rectangle which can cover everything. So we only have a finite number of things. So take the rectangle that can cover everything. Um,
Oh yes, and then the like if there are n gray squares, then those will like this process will also be white.
yeah. Okay, can you repeat what you said? I didn't.
It's like you said, take that rectangle which contains all these gray squares. So by this process, we can also turn that rectangle into whole white rectangle.
But how do we prove that? We haven't proved that yet.
Yeah,
Go on, Ahan. You.
Sentimentalidad,
Oh yeah.
sentimentalidad.
Yeah. So I was just take the
भाई मेरा
objective
One
to
second.
स्कूटर
show it.
दिलो का स्कूटर.
One second, Ahan. I'm really sorry. I just need to remove this first. Yeah. Go ahead.
this has happened
Yeah.
again.
Yeah.
So the objective to show is the right rectangle with 8 black squares that can be uh, turned into white in just 8 moves, right? So we have turned the whole 7 black square rectangle in 7 moves to white. Now the bottommost black square, if that is we can say that if it has both its top and bottom squares, top and right squares, all white. So just take those L termino and uh,
Yeah,
yeah,
yeah. So
and
what you're saying,
turn.
you're on the right path. Correct. Yeah. So what you're saying is that if these 7 are gone in 7 moves, as per the assumptions, then this one will be alone, and so it will go in the 8th move, right?
Yeah, yeah,
Right. For this example, it works. So, but in the general case, this might be attached to something over here, or there might be more than one blocks, right? So maybe what we can try to do is is in this rectangle, right? Okay, you know what? This is a little too messy. Let me actually go to another.
Yeah, big one, right?
Yep. Let me give me a second. Let me just
Yeah,
draw.
okay.
I'll just draw.
You're drawing with the mouse.
No. I'm using a stylus, but it's a very small device. For some
Yeah.
reason, my iPad didn't charge to fix it. Yeah. Oh yeah, but my work is still messy. Whatever I use. Uh, why is this person asking entry again and again after just doing that? Yeah. So, maybe something like this. Um, so if we want to show that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So in this case, I'm just saying 11. Okay. Um, then the argument I'm trying to formulate is that take the last row and last column out like this, right? Then say in this here, how many ever things are there, right? How many ever um, gray squares are there? In this case, we have 1, 2, 3, 4, 5, 6, 7. By strong induction, we are, yeah,
Yes, yes.
yeah. So by strong induction, this 7 will be done in 7 moves, right? Okay.
Yeah.
Right.
Yes, that is
This 7 will be done in 7 moves.
yeah, by our claim, by our assumption.
Yeah, right. By our assumption of strong induction, because we have assumed the statement is true for 10, 9, 8, and so on. Now,
This is
is it possible for us to create new gray squares in this area or this area?
so you are asking, is it possible to make these new gray squares in this area?
Yeah, Ahan, you can speak anytime you want to. Just speak.
Oh, okay. So the upper rectangle is all white, and if we wanna make another gray square, so uh, we have to find the two gray square in that L terminal. But as the right of that isolated black square and above of that all are white, so uh, new gray square can't be generated, I think.
Actually, a new gray square cannot be generated right after this has completely been converted to white space, correct? But before that's possible, you can probably create new gray squares like this. Here, this will happen in the next move and so on, right?
So yeah, this is by the statement.
No. I'm just making a general observation, right? I'm just trying to observe things
Okay, okay.
generally. Like I just don't want to give you the solution. I'm just trying to observe what I would observe normally in an exam,
Yeah, yeah.
right? So some of these things I'm maybe saying is misleading, but that's only because I just observe it and I just want to tell you. Right. This basically almost done at this point because look, you have some how many ever say 7 squares, and this will be done in 7 moves. And counting this, say I say call this rectangle 1, this rectangle 2, this rectangle 3, and the small square 4. Okay.
Yes.
So 4 will be done. Yeah. So 2 will be done in 7 moves. Then you'll have 1, 3, and 4 left. Now 1 cannot influence 3, 3 cannot influence 1, and the 1 has nothing to be influenced by 2, um, right? So it'll
Yes, like it is because that is far.
yeah, correct. So there's nothing to the right of 1 and nothing to the left of 1. Now, before the 2 went away completely, this 2 rectangle went away completely, it could be influenced because 2 is to the right of it. So you could probably make new ones and so on. But after that, it's not possible, right? Everybody with me so far?
Yeah,
Yeah,
at this up to this
Yeah,
point,
yeah.
yeah, it's clear.
Yeah. So, now let's say 2 finishes in some A moves, right? Um,
Yes.
Now, after 2, will now so we have a general idea. So first 2 finishes, 2 goes away completely, it goes to white. Then 1 and 3 go completely to white. And then finally we may have a block at 4, and that goes to white. Right? Now the thing is
Yeah.
at the
Yeah.
end, yeah. The thing is at the end, even if we don't have a block initially at 4, we in the second last move we may have something like you know, one thing here and one thing here. I'm really sorry for my horrible drawings. And you know, in the last move we may have suddenly have a block of a, you know, in the four, in the rectangle 4. So we need one move saved for rectangle 4, right? And so we basically need 1 and 3 to finish one move quicker. So the thing is, so let me just try to say what I'm saying. So in this specific case, you have 2 here, 1 here, and you had 1 here, right? And you have 7 here. Now these 7 finishes in 7 moves, right? In this case, I'm just giving you a specific example of what I'm trying to say. And this 2 and 1 happen simultaneously. That is, the first rectangle and the third rectangle go away simultaneously. They don't affect each other and they're going away simultaneously. Due to which, you know, you're not adding this 2 and 1, but this, after 2 moves, both the first rectangle and the third rectangle have disappeared. And then for the last move, this one rectangle has disappeared. So did you guys get this very specific example?
Yes.
Yeah, two
So
and
like
to white, then
you,
fourth obviously go to white.
Can you repeat what you said?
Yeah, you were trying to say that if the third means if the second and third, sorry, first and third goes to white, then fourth will definitely go to white because there
Yeah,
will be
4
no
will only
squares.
be one block. Yeah,
Yeah.
right. So, okay, for the general picture, okay, let's say you have this, that you take the rectangle of everything in it and you divide it into 2 rectangles like this. So let's say you have A blocks here, right? You have B blocks here, you have C blocks here, and you have, say, 1 or 0 blocks here. It doesn't really matter. Then in the first A moves, this rectangle will vanish for sure. Then whatever is greater of C and B, right? Whatever is greater of C and B, that will vanish in the in the next stage, right? So let's say B is greater, right? If B is greater, so A plus B moves, the only, after A plus B moves, the only thing that can be left is this one, and that will disappear in at most one more move. And A plus B plus 1 will be lesser than or equal to, you know, A plus B plus C plus A plus B plus C, because there is at least one block in C, right? So that's the gist of the argument. Did you guys get this?
The inequality, I think it went out of the sheet. Can you write it?
Yeah,
Uh,
I did. Oh, I
somewhere else?
didn't write it. Okay. Oh, you know what? Let me write this atop. A plus B plus 1 is greater than A, lesser than A plus B plus C.
this ordering argument is also necessary.
Can you say that again?
Uh, uh, is it really important that what is greater between B and C?
No, no, that doesn't matter.
Yeah.
No, here the thing is that 1 is greater than or equal to C, right? Here, greater than or equal to. That C has at least
Okay.
1, and that's how we're taking it, because
Mhm.
there's at least one block here. It is n square. It is only stable if the corner square. Give me a second, Dhruv. Let me read that. Okay, it is n square. It is only stable if the corner square or no square is gray. When another layer is added, it um, Dhruv, I didn't understand what you're saying. What is n square? Um, it is n square. It is only stable if the corner square or no square is gray. I'm not sure what you're saying, Dhruv. Um, can you speak up if possible, or clarify what you're saying? What is n square and what is stable? Yeah, okay. So we're done with this question. Dhruv, you can clarify what you're saying. Um, in the meantime, you can try this question, example 7, right? You guys can try it for a minute and we'll.
So in the previous question, actually,
Okay.
we took a rectangle and we partitioned it in such a way that since we had assumed that all the lower ones were true, so it would imply that the f of n will also be true. That only we did, no?
Correct. Correct. Correct.
Okay.
That's well said. Yeah. Dhruv, I didn't understand what you're saying. Is my voice still low? Okay, I seriously don't know why that's happening. Um.
It happens sometimes randomly.
Oh wait, it's happening randomly. Is my internet bad or something? Okay, now is it better now? Oh, I'm not sure why that is. Hmm. Yeah, you can try that once. Okay, guys, you can have you guys all just read example 7 once? Yeah,
Uh,
I'll just
yeah, I am reading it. Just
yeah,
wait,
okay.
like 1 minute.
Yeah, sure. In any case, I'd all suggest you have the handout so that you can look at the problem whenever you want to. It
Yes, yes,
always
from the
helps.
handout.
Yeah. Mm. Um,
It
Pranjal,
is
what
saying that
happened?
it is saying that 1 by n matrix has entries from this set. So this means that entries can repeat. I mean,
They will.
the elements of from this set can repeat.
Yes.
Okay.
Actually, in the previous question, I have an idea. Can you think? Do you think it's workable? Like, I'll just share it.
Yeah, go on.
So we assume any random coloring of this graph, and then say we choose a random rectangle in which there exist such white squares which are between black squares. Means there exists cavity between black squares. So if we consider that cavity I'm referring to white square. So if we consider that cavity, then we can color all the cavities in such a way that we have a closed figure which is only made of black squares. So after that, we can reduce that. We can pick all the corners of that closed figure and slowly turn all the black squares into white one by one. This is always workable, I think.
That's a very interesting idea. I have to okay, wait, let's actually try that out. So can you okay, so go on, can you just repeat that idea once?
Okay, so we have a random coloring of the graph, and there are and there exist some cavities. So this is the case one. So there exist some cavities between black squares. So
Right.
we always can cover the cavities between black squares. We can always turn that cavity into a black square so that we have a closed figure in which all the edges and corners, everything is filled with black square. This is the
All the
this is
all the edges and corners? Okay, so
for example.
you're asking me to wait, you're saying fill some white squares as black squares?
Yeah, you can fill it in any random way. It doesn't matter.
No way. Right. So no, let's say it's something random. That doesn't matter. Okay, so what do you say?
So I was trying to say that so we can consider grids in such a way like for the first two squares we can consider a 2 by 2 grid. In that there exists a white square. There's a cavity, so that cavity can be turned black. So yeah, that cavity will be turned black, and then we will have a case of closed figure where all the where everything is filled with black. So we will consider the corners one by one, and all the corners will turn white because the surrounding squares will be white.
Wait, and how do we know that this smaller part will not be influenced by something bigger?
Yeah, I was going to say that.
How do we know that?
this thing will, later on not be influenced by something bigger, like something outside it?
We will consider the maximum possible grid, which considers all the which contains all the black squares in it.
Right, so that's basically the same idea, right?
Yeah, I think same.
You're basically taking a grid, and I'm not 100% sure of what you're saying, but you're taking a grid such that it can't be influenced, a smaller grid, and you're showing that, you're assuming by induction or something that it can't, it will reduce in some number of moves, and the rest is just figuring out the details that stuff will work out.
Yes, we will consider. We can construct all the closed figures in whatever square or rectangle which we'll consider, and then the corners can be easily turned to white one by one.
Okay, I'm not 100% sure of what you're saying, but um, I think you have the right idea, and you just need to, right? So
I think it's
maybe
like
you're saying,
similar only to previous idea. I think it's workable.
yeah, it might be workable. It doesn't sound wrong, but I'm not 100% sure of what you're saying. Um,
Okay.
Pranjal,
Oh,
I'm
will
really
you
sorry to reply late, but
will you write this your idea after the meeting?
yeah,
Okay.
sure.
Yeah, that would be good.
Um, I'll I also think that you should be able to find some sort of solution, guys. Just, yeah, you can again go through example 7 for one more minute. Start trying the question, right?
Okay.
Yeah, yeah. If you have anything else for the previous question, do tell. And guys, Dhruv and I forgot who else just said. You guys, if you guys would, try this thing, maybe write up whatever you just said, in a better way, and
Yeah. Okay. I'll attempt a solution.
yeah, great. Yeah, Akshay, yeah, right. Pranjal, I didn't understand what you had said before. Something about sharing the link. That's okay, right? Sharing the link.
So this problem in 7 is has a setting like Sudoku.
Oh yeah, you could say that. I don't know. It's different, of course.
Yeah, it's pretty much like Sudoku.
It is kind of different. In Sudoku, you're only saying that every row and every column should have stuff from 1 to n. Here,
Yeah,
you're
yeah, yeah.
saying the row with the column. Yeah, yeah, but
So will
you could find some similarity in structure. I think. I'm not sure. Okay, let's just try writing down something. No, maybe let's try looking at. Um, let's try with a. Let's try a 2 into 2 grid first. So we are saying that so for n is equal to 2 in this case, so 2n minus 1 will be 3. So we need to fill the numbers with 1 comma 2 comma 3, such that the combination of the first row and first column and this combination of the second row and second column all have 1, 2, 3. And in this case, it's very easy to figure this out, right? So this might be, you'll get used to what I'm saying.
Yeah.
You'll get what I'm saying very easily. So look, this is the first row plus first column. It has 1, 2, and 3. And this is the second row and second column. It has 1, 2, and 3 as well. Right?
Yes.
So for the sake of making stuff easy for ourselves, let's call the combination of the first row and first column. What do we call it?
Special.
No, I mean it needs to be an object, right? We can't call it the first special, the second special. Okay, yeah, why not? So the first special, which is the combination of the first row and first column, contains 1, 2, and 3. The second
When
special,
it mentioned that all that the set S should be exhausted, they're saying that the entries come from the set S.
um, contain all the members of S.
Okay. I thought it is to prove statements. Sorry.
No. This is somewhat of a construction question, and construction questions usually, construction questions have this usually, the thing is, it sort of feel. Hopefully, you sort of get this feel that you can sort of induct in some sense because when they're
Yeah.
saying
And
that,
in this question is look pretty much like we can induct because like for showing for n and then n plus one.
yeah, it need not
Is
be for
it
any.
that
Yeah.
even and work, odd and don't work except one?
I'm pretty sure odd doesn't work. As as a
Yeah.
matter of fact, that was part of the original question. Something like
Yes,
showing that
1997.
1990, yeah, doesn't work.
Or powers of two or even one of these work, I guess. Not
Yeah,
sure.
I'm pretty sure only powers have to work, but let's try to get that somehow, right? And as a matter of fact, if you try to if you tried for 3 into 3, and I actually asked you to start, try once.
Yeah, I tried 4 into 4.
Were you able to get some? Were you able to make it 4 into 4?
Yeah.
Nice.
Yeah, 3 into 3 doesn't work, 4 into 4 did work.
Yeah.
Oh,
Right.
3 into 3 doesn't work means we cannot make 3 into 3. Like there does not exist a silver matrix with 3 into 3.
Correct.
Yes.
Okay.
Okay. Something's wrong with my. Okay. What's happening here? Oh. Okay. There's this huge delay. I'm sorry, guys. So I'll just wait the delay out. Right. So yeah. So you guys can try it out. I implore you to try this thing out, and you'll realize that for 3 into 3 it's not possible. And I didn't include that part of the question. Saying that showing that odd doesn't prove because that's not exactly induction-y. But I want to concentrate on this part. And unlike the previous question, we tried to prove something, and we found some part of a thing. We went and found the part of the thing, and we divided. We made the parts ourselves. Right. So we
Yes.
found, yeah. So we found something. We only divided. We only made the parts, and we only used induction to prove it. Right. Our strong induction was on the number of gray things, but
A number of partitions and then adding up.
no, the number of partitions was always 4, but our induction was on the number of gray squares.
Oh, yeah,
It was
yeah.
a strong induction on the number of gray squares.
Yes.
Right. In this case, what to induct on might be a little more obvious, But the thing is, it's not even obvious that we need to do induction. So we're trying to do a construction problem, right? We're trying to construct something, and you know they're sort of asking us to construct something for all n, and this might not need induction. This usually doesn't need. But the thing is that what if we can use some lower value of n to create a higher value of n? You know, um, this might be what I'm about to tell you might be a very bad example, but I somehow I just connected it in my mind. Um, the contradiction proof for primes. Um, okay, yeah, you know what? That's a very bad example, but yeah, in any case, um,
Yes, yes.
yeah. So give me 1 second. I'm sorry. Okay, my app isn't responding. Wonderful. Yeah, so I'll just use the mouse or something. Till then. So yeah, So they're asking we want to construct something from n, and it's sort of maybe you can use the we can use something that's been constructed previously to construct something new, and that's the idea over here. And I probably shouldn't have said it, but in, these are questions in which you should probably try for a long time, and you know yeah, you should probably try for a longer time. So, and we don't have a longer time. So this is a normal. This is a useful idea. Could be useful. Um, to make a construction, we use a previous construction because it often has the properties of the previous thing, right? Okay, let me try to do something about this. Yeah, yeah. Time for drawing with the screen. Yeah. So yeah. Um, I was just about to draw 3 into 3 and try to try some things. Try to try a few things out. See if 3 into 3 works. But I'll just tell you this straight. 3 into 3 doesn't seem to work. You know, and actually, what? Just to be completely honest, construction questions are usually not a good thing to speak about in a class. Because you get it in 1 second, or you can get it in 10 or 100 or 1,000 or whatever. You have to figure it out, and it's hard to explain the intuition behind constructing something. And when you show the construction, it feels like magic. But this one's slightly better, but yeah, just a general thing. So that, right? So if you have a 4 into 4, now you need everything. Yeah, you need everything from
7.
1 to 7, right? You need anything in 1 to 7 from the
Yes.
first special, and the second special, and the third special, and the fourth special. So this plus this you have 7 things here, and it must be filled with 1 to 7. So you can't repeat anything in the first row to the first column, right?
Yes.
Um,
Yeah, that is why I said this is something like Sudoku.
yeah, something like that maybe. But in Sudoku, if this was Sudoku, you'd only have 1 to 4.
Yeah, and not completely something.
Yeah, something. Maybe you could say that.
Yes.
The structure feels similar, right? You have some sort of condition about the number
Yeah.
of things. Yeah, and you're filling in numbers and grids. So a very important, actually, this is a very important idea when doing construction questions, is to keep some sort of pattern, right? Trying something random doesn't work, and usually there will always be some sort of symmetry in the question, something you can learn about and implement, right? Usually when you're trying to prove something is possible, and the approach you're trying, is by constructing it to show that it is true. Um, this is what you can. There's something to keep in mind that use some symmetry, something like that, right?
Oh,
Try to
okay.
keep things. Yeah. So again, that sounds really vague, but you can't tell anything very specific in general by definition. Um, so maybe I can have a 2 here. I might as well have a 2 here because I have to have a 2 here, and have to have it. The thing is, I can just fill this up with 1, 2, 3, 4, and I'm gonna put the 5, 6, 7, 8 here. 5, 6, 7. Um, and you'll notice that I have to have 1, 2, 3, 4, 5, 6, 7. And interchanging 2 and 5 everywhere in the grid doesn't matter. These 7 can be represented by 7 colors. You can interchange this with 7 letters. These 7, 1, 2, 3, 4, 5, 6, 7 I've written are just labels, right? So you can put them in any order. And since in the first row and first column, I have to have all 7 things, I can just put them somewhere, right? I'll just put them. And I'm just trying
Yes,
to
and
construct.
by our yeah, and by future needs we can just swap them.
Yeah, right. Um. So we need to figure out something to put in this square. Um. This one. Um. So what do we do about this? So
Like we have
Oh,
options, so we
for
can
the
start
four
with
by
anything.
for four
yeah,
by five, I found a like good matrix which looks good, but not sure if it is very good. Like, shall I tell it the matrix?
4 by 5.
Oh, 4 by 4. I mean,
Oh yeah, yeah. Go on.
okay. 1, 2, 3, 4. Then 5, 6. Leave the space 3.
Wait. Here is 6.
Yes, I'm speaking row wise.
Right. Okay. 5, 6.
Leave the space and 3.
Okay.
Yes. Now in the next row, 6, 4. Oh, like
6.
yes, 4,
Hmm.
1, 2, and then 7, 1, 5, 6. Okay. Yeah, 7, 1, 5, 6. Can you just erase that third row 4?
Okay. This. Wait. Does this work? And third row here is 4.
Here, yeah, here is 4 or
No,
7 and
I
come.
think we'll have a 7.
7. Yes, yeah.
Okay.
So
Does
like
this work?
yes, I checked it. I guess it did work. Yeah.
Yeah, it
No, I
works.
guess
Oh,
I
what?
think it
oh
works.
yeah, like here.
Yes,
Yeah,
it does
this
work.
works. Yes,
Here
yes.
the
Yeah, you have to
It
check
does
the
work, right?
third row and third column. Yes, this works.
Amazing. Yeah, yeah, yeah. This works.
oh, okay. I did say the wrong matrix, but this also works. Sorry.
What's the matrix you were looking for?
Yeah. Can you just draw once more? Sorry to trouble.
Oh, that's okay. Yeah.
I mean, this also works, but like the nice looking, I meant basically.
Right. This looks pretty random. So
Yes. Yeah.
this doesn't generalize easily. Yeah, go on.
Yes. 1, 2, 3, 4.
1, 2, 3, 4. Yeah.
5, 1, 4, 3.
5, 1,
4,
4,
3.
3,
6, 7, 1, 2.
6, 7, 1,
1, 2.
2. Yeah.
Yeah. 7, 6, 5, 1.
7, 6, 5, 1.
Yeah. So like the thing which I noticed in this is the diagonal elements in one diagonal are 1.
Right.
And if you notice that this is symmetric, no? 1, 2, 3, 4, then 4, 3, 2, 1. Like if you just see the end rows, then 7, 6, 5, 1, 7, 6, 5, 1. Like in some sense, I found this symmetric. So I thought like maybe symmetry somewhere is used.
So yeah, right. So you're saying you made it symmetric along this
Yes.
axis.
Yes.
That's a nice symmetry to make.
Oh yeah. Yeah. Can we generalize this? Oh no, I mean we cannot say this right now.
So this looks very nice.
Yeah,
Um,
very nice.
I have also one more kind of symmetry. Can I tell it?
yeah, sure. Let me draw once more.
Oh, also, like, just as a suggestion, you can like copy the slide. I guess so. Not sure.
No, it's okay. What's the point? Like we'll draw new ones for all the new ones anyway.
Yeah.
Yeah, go on, Akshay.
So start from the bottom left and put 1 to 7. 1, 2, 3, 4, 5, 6, 7. No,
Whoa.
no, 2 should be above 1. Okay, it
Okay.
doesn't matter. For
No,
here,
wait.
2 should be
It's
above
okay.
1.
It's okay. It'll be more comfortable for you if we do this. 1, 2, 3, 4, and here 5.
Yeah, 5 should be after 4, right on the right.
Here.
Yeah, 5, then 6 on its right and 7 on its right.
Okay.
Then after 1, there in the bottom, after 1 there is 2. Then after 2 there should be 4.
After 2, 4.
Yeah, then
Okay.
3.
Okay.
Yeah, then 3. Then
3.
above 3, 5.
Here 5.
Yeah, 5. Then 6. Then 7. And in the middle 4, you fill above 2, 1. To right of 1, put 3.
Okay. And I see.
Above 3, put 7. And left to 7, put 4.
This works as well. I think. No, there seems something wrong. Is this correct?
Yeah, globally this is also like random.
Oh yeah, never mind. This seems correct.
Oh no, like just see the third row and third column. 4 is
Oh yeah,
common.
this is wrong. Look. Oh yeah. So something seems wrong about this. I think.
Yeah.
Is this?
Third row
I'm
and
not
third
sure.
column.
Yes,
Third
4
row,
is
third.
common. 4 and 3 are common. Oh, wait,
No.
what? Okay,
No, it's
I was
third.
saying opposite. Never.
Right. Never mind. It's correct. I'm sorry about this. It's
Yeah,
correct.
yeah,
Yeah.
correct.
Yeah. It's correct. Right.
Yeah,
And
one, two, three,
what's the
one, two, three,
symmetry
four,
you're
five.
talking about?
Actually, little bit. Sorry, there was not such symmetrical. But I was trying for for 6 cross 6, and I think that the way I put 1, 2, 3, 4, 5, 6, 7 from left to top. If we reiterate it towards the bottom to right, can you get a symmetry of such?
Um, I'm not sure.
So we have to check like for 6 also.
But in any case, I think we might be able to generalize stuff like this. Um,
Like this which Pranav gave, this is like quite asymmetric. So can this be generalized?
the second one, right? It's this one, right?
Yeah.
Yeah. So I think you should be able to make something general out of this. Especially
Can
that
we? Yeah. Can we take another example? Like we know that 5 does not also like. So can we just see 6? But that would take some time.
yeah, like my idea about this was to introduce to the fact that constructions in general can be used using induction. And I just want to try at least something else before ending because I just don't want to end on this. Now I'm conflicted between just telling you the answer and letting you
Yeah, you
draw
tell
the
the idea because only 10 minutes are remaining, I guess.
yeah. So I'll just tell you the basic idea, in which is something I should not do, but I'm gonna do anyway. Um, the idea is if you replace say 3 and 5 here, right? I think this is a proper thing. And excuse me for overwriting and something like that. You'll notice that our original 2 by 2 thing that we worked with, 1, 2, 3, 1, comes up here and here, right? And at this point here, we've added 5, 4, 4, 5, and 6, 7, 6, 7, 7, 6. So maybe you can try something like that. You can try putting up stuff like this. You can maybe use one of these to make a 8 into 8 where you put this over here and this over here. Because and why is this seem like a good thing to do? Look, if
Oh
you're
yeah,
looking at
because
the first,
that generates that makes the square bigger.
Yeah, but not only that, that's like not the only idea why I'm saying that. Um, the thing is, if you say add two four, like you put together four into fours, and such that your with the 4 into 4 we generated are in the this thing and over here, right here, then the first row and first column will have everything from 1 to 7 because of this, because the way we added was to make sure that everything in first row and first column is from 1 to 6, and so will every row and column. They will have everything from 1 to 7. Correct? Because even now, if you take the last row and last column, we made sure that this, you know, can you see what I'm
Yeah.
trying to say here? The last row and
Yes.
last column will have everything to 1 to 7 because of the fourth section, because of section 4 here.
Yeah. Yeah. Good.
This is 4 by 4, right?
No, I'm saying like this is a 4 into 4. Each of these big squares is a 4 into 4,
Oh yeah. Okay.
or it could be anything for that matter.
Yeah.
Right. Right. It could be anything. Um, the idea is that if we put if you put those two squares in these case in these places, um, then what will happen? Um, then you'll notice that
But then, uh, let's say we put in these four partitions the 4 into 4 matrix which we obtained earlier. Then what happens is that only 1 to 7, 1 2 3 4 5 6 7 will repeat in all the fours. But here we need, like this is 4 8 into 8, so we would need 2 into 8 minus 1, like 1 to 15. So we have to change like
correct.
that.
So that's why I'm saying only put 1 to 7 in this one and in this one.
Okay.
So then we can
So
just
that's enough,
replace
right?
1 by 8 and 2 by like this stuff, no, and put it there also in the
Right. That's the
remaining case.
basic idea. If
Yeah.
you and we want to make sure that you just add whatever 7 to all the numbers in the grid, and you put them in the second and third in these two squares, right? And if you don't try what I'm saying, you probably think this is a little vague, but I'll just show you exactly what I mean for
Yeah,
oh
this is
wait
clear.
sorry yeah, so in any case, I'll just show you a quick example of what I mean. So add 2 into 2 squares, right?
Okay.
um to make the 4 square what we're saying, right? So I'm saying write down 1 2 3 1 like this. Now when we wrote these two down, we made sure that everything has 1 2 and 3. Now we need to make sure everything has 4 5 6 7. And in that
Yes.
case, what do?
Yes.
Yeah, and that's not hard to take care of, because um doing something like 4 and 4 suddenly takes care of everything, that every row and every type of section, the first row and the first special, the second special, the third special, and the fifth special, they all, like all the four specials have 4. Right now it's taken care of. Similarly, if I do something like 5 comma 5, you're done with that. 6 comma 6 and 7 comma 7. Now this might seem a little vague, but you can try generalizing this, right?
Yes,
And
like we use 1 to 3. So in the same way, we can make grids with 4 5 6 7.
yeah, we can do that as well, right? The other thing we can do is we can do 4. Oh, um so wow, my thing is horrible. Let me yeah. So instead of doing what I just said, we can do something like, I just wanted to figure you to figure that out on your own, but we can instead do something like, we can put a 4 5 and a 6 here, and something like a 5 a 7 and a 7. Oh God, give me 1 second. Yeah, you can put a 7 and a 7 here, and again a 5 and a 6. It's up to you to figure out a general pattern, and I'm sure there are quite a few ways of generalizing. But you can see the general idea. That is, we're using the fact, we're somehow using the fact
Like
that,
a smaller square to get new to
yeah,
generate
we're
new
using the
squares.
same property. Yeah, right, right. So, it's just one idea that you can prove a construction using, you can use induction for to make constructions, not proving constructions. I'm sorry. Um, right. So moving on. Um, Example 8 is just a puzzle. I actually have no clue why it's still there. And I don't think we won't do another problem, but maybe I can just explain a few ideas. Um, it's not a good thing because you're supposed to usually give problems with ideas to make those proper. But in any case, graph theory, and in graph theory is simple for anybody who hasn't studied it. It's just a few bits of terminology. Shouldn't be very hard. It's just having you just have points called vertices and edges that connect them, and you study these kind of things. And in general, graph theory is especially prone to induction. You might have studied this, you might have seen that here and there, but it's a good thing to know that when you have something that can be written in the form of graphs, induction is something to try, right? um, because and the reason for that is because of something we discussed initially, that induction is good only with discrete objects. In some sense, you need to have some f of 1, f of 2, and so on. And in graph theory, you have n vertices, or you can make that n minus 1 vertices, and so on. And so induction works well with graphs. So you can try these 3 questions. They're all really nice questions, right? um yeah, so is that about it? Is there anything else I wanted to say? Right. So induction works well with discrete objects. There are probably a couple of things I could say, but it doesn't really matter all that much right now. Yeah. So does anybody have any questions? Maybe about the question that I rushed, or anything else at all? We'll end here at this point. So anybody, anything?
Yeah, the symmetry which I just showed you in 4 by 4, I'm not sure, but I think it also should lead to a solution in 2 to the power k matrix. Not sure though.
It should, right? So it's the thing, right? We're adding up four into fours, and then we're adding up four thing into this. It should work out. Try
Oh,
it.
no, no, not that. Like the symmetry which I showed you, know, of that. Like, can you just go back to the previous slide?
Give me 1 second. Yep.
Oh,
This one.
yes, like it had symmetry, 1, 2, 3, 4, and then 5, 6, 7, and then that symmetry, diagonal symmetry I'm talking about.
1, 2, 3, 4, 5, 6. Wait, which one are you talking about? 1, 2, or 3? Which rectangle are you talking about?
The first one in which you didn't replace 3 and 5.
Okay, yeah, okay, right. So you had
Yeah.
1, 2, 3, 4, 3, 1, 4, 3.
Oh,
Yeah.
okay. Just a second. It was
Yeah, 1,
1,
2,
2, 3, 4, 5,
5.
1, 4, 3.
Yeah.
1, 4, 3, 6, 7, 1, 2, 7, 6, 5, 1.
Hmm.
Yeah. So in this, like, there was a diagonal symmetry, right? The diagonal which you have made symmetry according around about this.
Right.
Yeah. So I'm just saying, like, okay, if we consider a bigger matrix, 8 by 8, we just keep the boundary elements like 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, like all the elements. And suppose at a random place, if we put an element, just say 2, like at a random empty space, I'm saying.
Hmm.
Okay. So if we just take a symmetric, like symmetry about that axis, and put that 2 there, I think that should also work. Like putting the
Yeah,
elements
that might
this
work.
way.
Yeah, something like that might work. Like you don't need to induct. Like you can construct generally.
Yeah, that's what I'm saying. Actually.
Yeah. And of course you can do that. That's the whole point of the server. Yeah. Anything else? If you have questions, you can ask. Yeah, go on.
No, not really.
Oh, okay, yeah. So, I mean, if you can think of some solutions while trying the questions, if you can think of solution, or if you have questions while trying the questions again later on, you can ask in the survey, right?
Yes.
Right. So we'll end at this point then, right? So thank you all for listening.
Yeah, and